Hello, welcome to part 3 of our lecture on connective tissues. Now, just as a quick reminder, I want to point out that connective tissues are very different than our other tissues in that when we're looking at connective tissue, it's really all about the extracellular matrix rather than the cells. Now let's go ahead and take a look at the functions of connective tissue. Connective tissue can act as a structural framework. Obviously, things like bone and cartilage are great for this. We can transport things with it. Blood and lymph are both connective tissues. Of course, our skeleton can provide physical protection. We can bind structures or surround structures kind of in an envelope with our connective tissues. We can actually store fat in our connective tissues. Adipose is a connective tissue. And because blood is a connective tissue, our connective tissues can help to provide our immunity. This would be the job of the leukocytes or white blood cells. So we're going to take a look at the 3 basic components of connective tissue. Connective tissue consists of cells, protein fibers, and what we call a ground substance. Now obviously there are some cells in there, and we want to take a look here maybe at a fibroblast here, kind of one of the important cells of connective tissue. Although this really depends on exactly which kind of connective tissue we're looking at. Fibroblasts are going to be active in producing fibers within these connective tissue proper that we are seeing here, and we're going to take a look for things like osteocytes or chondrocytes within some of our other connective tissues. Now, the extracellular matrix is the combination of the protein fibers and the ground substance. In other words, it's the stuff other than cells. So as we look at this particular connective tissue, we can see some collagen fibers running a bunch of different directions in here. There are even some elastic fibers in here, and they show some reticular fibers in there as well. So those are going to be the fibers that are going to be providing some of the strength of this connective tissue. And the ground substance, in the case of this being a connective tissue proper, is simply going to be a fluid. That means that this tissue is largely defined by the protein fibers, and it's going to be pretty flexible, although the degree of that flexibility is determined by which type of protein fibers are in there and how many of them there are. But when we move on to things like cartilage and bone, the ground substance is going to become thicker, and it's going to start to have more of an effect on the nature of the connective tissue. So, as we close with this slide, when we think connective tissue, we need to know what the extracellular matrix looks like. That's going to tell us the properties of the connective tissue. All right, so there are some basic categories of connective tissue. We have connective tissue proper, which has a fluid ground substance. And so we need to, again, take a look at those fibers. This includes things like fat and tendons, and obviously they are going to differ in the density of the fibers. We have supporting connective tissue in cartilage and bone. We're going to be taking a look at that in this chapter as well. And over here we can see the difference between this hyaline cartilage with this rather solid looking matrix and this up here where we have some areolar connective tissue where there seems to be a lot of space because of that fluid ground substance. Now our final category down below here is in this case blood, but blood and lymph connected as fluid connective tissue, and we're going to cover blood later on in the semester. So within the connective tissue proper, we have 2 basic categories as well, loose and dense, which relate to the amount of the protein fibers that are in there. So loose means that those protein fibers are loosely packed. This is going to form actually some packing material or some tape in various places, but it's not incredibly strong because we don't have that many protein fibers. It's going to fill spaces, it's going to provide some cushioning and support. It may be a loose binding for some things. For example, one of the things we can do with this loose connective tissue is basically tape together an artery and a vein which run alongside each other. Now, dense connective tissue, on the other hand, is going to have a high density of protein fibers. And we see that down below here with dense regular connective tissue. So in this case, it's regular because all of the protein fibers are going the same direction, and this tissue is mostly protein fibers. So this is going to provide some strength and resist pull. In the case of this particular one, since all the fibers go in one direction, it's resisting pull in one direction. So let's go ahead and take a look at some of these connective tissues now. We're looking only at this point at connective tissue proper, and we're going to start here with areolar connective tissue, which is again going to be loose. We see a couple images here, and the fibers are not tightly packed for the most part. They're rather far apart. That's going to give this thing a great deal of flexibility. As we start to think about where it's located, that flexibility is important. This is found in what we call our subcutaneous layer and superficial fascia. Now, the subcutaneous layer is the layer that is under the skin. Our skin is composed of the epidermis. Now, we've already learned a little bit about the epidermis. It was composed of keratinized stratified squamous epithelium. Then below that is the dermis, and the dermis is going to be the relatively kind of tough, thick layer of our skin. And under that is the subcutaneous layer, which will bind it to the underlying musculature. So to understand how this subcutaneous layer works, pinch your skin and try to wiggle it around over your muscles. It should wiggle around relatively freely because areolar connective tissue and adipose tissue will be the tissues that fill that subcutaneous layer. So again, the reminder here is it is loose, it moves freely. It can be used as a tape or a wrapper to bind stuff together with good flexibility. And it does form superficial fascia, which makes us say, hey, what in the heck is this fascia stuff? Well, it's a shiny layer of binding tissue. It tends to surround and separate muscles or vessels, and it really depends which particular kind of fascia you're talking about because it comes in superficial and deep forms, and they are actually made of different kinds of connective tissue. So superficial fascia we see here. Some of this has some adipose tissue in it, so the adipose is the yellow stuff, and that white stuff you see peeling off of the muscle of this cadaver here is going to be our areolar connective tissue. Now down here we can see this a little bit closer, and you can see that it's kind of peeling and tearing. You can actually do this by hand. You don't need a scalpel to cut this kind of stuff. And you can actually pull on the skin and kind of hear this stuff ripping as you go. But that's a great example of superficial fascia. Now again, we will also see this wrapping blood vessels together, and we'll talk about that later in the semester. The deep fascia, which we see over here, obviously looks thicker. This is composed of dense regular connective tissue, and it's going to be very strong. This is basically the same stuff as our tendons, but it often forms these sheaths which surround muscles, and often they are actually part of the tendons which help our muscles connect to bone. All right, next we have adipose tissue. If you take a look here at this adipose tissue, you're going to see all these big chambers here, which kind of look empty. Now, if we find one like this one, which is really nice, I can see a nucleus right there, and this is all plasma membrane around here. This is an adipocyte, which just basically means it's an adipose cell. And it looks empty because we've produced a slide of this and we don't see the three-dimensional lipid glob that had filled up the middle of this. But these cells are basically cells which can store lipids, and as they do so, they're going to push the contents of the cell towards the outside as the lipid ball grows in the middle of it. And that leaves us with this, what I kind of think of as a pink chicken wire kind of appearance. Now, if you look in between the adipocytes, you see some little squiggly stuff. That's areolar connective tissue because adipose tissue is essentially areolar connective tissue with all these adipocytes in it, which are storing adipose. So the question is, where do we find this stuff? Well, we found areolar connective tissue in the subcutaneous layer. We find this stuff there as well. Now, how much of it you have largely depends on the balance between the calories you take in and the amount of energy you expend. And where you store your fat often is kind of associated with your genetics. You likely store it somewhat in the same places that your parents did, although we do see some kind of differences in storage location between males and females as well for the most part. We also have some of this adipose stuck around our kidneys protecting them, and almost any open space you can find in the body. The back of your eye socket, under your kneecap. We have globs of fat in those locations as well because it can also serve a cushioning function as well as that kind of fairly long-term energy storage function. All right, our next tissue is reticular connective tissue. Reticular connective tissue is a little bit more kind of specific in its location. and it has a different fiber in here. That's these black fibers we see, which are reticular fibers. You see a lot of space as you look in here, but there seem to be a lot of cells packed around here in between these fibers. This is a little bit zoomed out kind of view of this, and this is what we might see if we take a look inside an organ which is formed of reticular connective tissue. Now when I take a look at these little black fibers kind of squiggling all over the place, it creates kind of almost a maze-like environment. So we want to think about that as we think about these organs that are going to have this. Reticular connective tissue is found in lymphatic organs, part of our lymphatic system, which is associated with immunity, as well as kind of returning excess interstitial fluid back to our cardiovascular system. So when we ask ourselves what's going on in these places, if this maze-like environment exists and it's in a place like, say, our spleen or our lymph nodes, we're going to have some pathogens moving through the fluid, blood in the case of the spleen, lymph in the case of the lymph nodes, and it's going to work through this maze-like environment where it's going to interact with some white blood cells that are in there that might actually end up killing a bacterium or other pathogen that's floating through that area. Now this also forms our red bone marrow, which is the area where we end up forming all of our blood cells, usually in some of our flat bones or the proximal epiphyses of some of our long bones. So what is this thing doing? The fibers support the organ. If you've ever poured concrete, you might add rebar in there to help support the concrete, and it's doing kind of the same thing. But again, where we do have flow, it's also allowing for flow to occur through that organ, and it does give this opportunity to have these kind of battlefields for our lymphatic system. All right, so we're on to dense connective tissues, and again, we're going to see some fibers here, lots of fibers, relatively little space as compared to those loose connective tissues. This is dense regular connective tissue because the fibers are all running the same direction. That means that I have an attachment site up here somewhere, an attachment site down here somewhere, and the pull is going to be from those two different directions. So when we think about this, the dense means this will be strong because there are a lot of fibers. The regular means all the fibers go in the same direction, which means that that strength is in one particular direction, and we find it in places where the pull is in a single direction. In tendons, where we're going to have muscles attaching to bone. Ligaments, where bone is attaching to bone. And of course our deep fascia, which can be serving as a tendon or serving similar functions. It can actually bridge from bone to bone as well, but also forms a nice wrapper which will compartmentalize our limbs as well. This looks more like a mess. So there are certain tissues which are kind of confusing when you first look at them, and then you kind of learn to interpret that confusion as what this tissue is. I would say that that can apply to things like pseudostratified tissues. They look a little bit messy, and dense irregular connective tissue looks messy as well. But if we break down the name, we should be able to make some sense out of this. Dense means that this should be tightly packed with protein fibers, primarily collagen fibers. And we definitely see that there's not a lot of open space here, so dense perfectly makes sense. Irregular means that those fibers are going in many different directions. And that's where we get the kind of weird look to this. Almost looks like a finger painting or something like that. Some of those fibers were coming directly at you. Some of them were running diagonally. Some of them were running up. Some were running across. And when you slice through this, you're going to be slicing them in all kinds of different ways. So you're not seeing the fibers all running in one direction as they were in dense regular. So then we just have to ask ourselves, where do we need a lot of strength but in multiple directions? So again, remind ourselves, dense is strong, irregular, many directions. This supports our dermis. Our skin has to move in lots of different directions but still needs to be relatively strong. And then the periosteum and joint capsules. So the periosteum is exactly what its name says. Peri means around, osteum says bone. This is a wrapper that wraps around our individual bones. And when it gets to a joint between two bones, it leaves the bones and becomes the joint capsule, eventually connecting to the other bone on the other side of the joint. So our joints might need to move in multiple directions as well. Okay, elastic connective tissue. Those little black fibers in there are elastic fibers. They clearly are dense. In fact, they're all kind of running the same direction as well. So some people see elastic connective tissue as a specific form of dense regular connective tissue. Now, we're not going to treat it in that manner because it's definitely located in specific locations which are based on the elastic fibers that it has in it. And you notice they're squiggly. It's like they're springs and they're not currently stretched out. So what happens with this is it can stretch, but it's going to snap back to its position the way we see it now. So we need to think about places that are going to need to do that. So to stretch and snap back, we're going to provide what we call compliance to our arteries. Now, when you think about that, if your ventricle contracts, you're going to force blood from your ventricle into the large arteries that are near your heart, and they are going to need to stretch as that pulse of blood travels through that. And once the pulse has gone past, they're going to kind of return back to a smaller diameter, and that's going to help the blood continue to move towards its destination. So this idea of compliance in our vessels really relies on the elastic nature of our large, or what we sometimes call elastic, arteries. Now it ends up we have this in a couple of other locations. We do have this in the suspensory ligament of the clitoris or penis, which just kind of holds those things onto the symphysis pubis. All right, so we are into supporting connective tissues. We have hyaline cartilage here, and the big difference we're expecting to see right now is that we don't have a fluid ground substance. We have a gelatinous ground substance, and therefore when we look at this matrix, it looks solid. I often look at this and I'm like, wow, that looks kind of like a plastic version of Swiss cheese or something like that, because we've got all these holes in here. This is actually a younger version of hyaline cartilage down here, a lot more holes and less of that solid material. So we want to kind of explain what that is. The things inside of the lacuna, and that should probably actually have an E on it and say lacunae because I'm pointing at two of them. Lacuna is one, lacunae would be plural. These are the holes in these somewhat solid supporting connective tissues, cartilage and bone, where the cells reside. And these cells, in this case, start out as chondroblasts, which are going to actually secrete the matrix. So they start secreting the solid substance around themselves and basically wall themselves into this lacuna. Same thing's going to happen in bone as we start to form that. So as this cartilage matures, we end up with more matrix, and these lacunae are further apart from each other because they have, during that growth process, been secreting more matrix. So where do we find this hyaline cartilage? Well, it looks pretty smooth, right? We don't see any fibers in there, and that's really key. It does have collagen fibers in it, but they're very small. So this is both our most rigid cartilage and our smoothest cartilage. And where do we find it? Lots of places. So we find it in our trachea and our bronchi. When we talk about our trachea being held open by C-shaped cartilaginous rings, they're made of hyaline cartilage, which are nice and rigid. You can actually feel your larynx, your voice box, just kind of push on where you think your Adam's apple is. Nice and solid. That's made of hyaline cartilage, as are your costal cartilages that connect your ribs to your sternum. You have thinner plates of this in your nose, so they're a little bit more flexible. And as far as the smoothness goes, we have this on the articular surfaces of our bones. This is the cartilage that forms that joint surface. It's the cartilage that gets damaged and then ends up giving us arthritis. So we do have this in a couple of other places. It starts out for most bones as cartilage in our fetal skeleton. And we convert that cartilage into bone, leaving cartilage on the articular surface. And until we reach maturity and stop growing, we leave it at what we call the epiphyseal plates. The epiphyses are the ends of our long bones, and the epiphyseal plates are basically slabs of cartilage in there which allow those long bones to continue growing in length until we reach maturity and convert that into bone. All right, so what exactly is a lacuna? Well, here we can see it in both cartilage and in bone. And these are spaces within the matrix of supporting connective tissues where the cells reside. So these black spots we see on this microscope photograph of bone, those are lacunae. There's actually what we call a central canal in here. And here we see cartilage where chondrocytes reside inside of lacunae there. Now, it's a little bit harder to see these lacunae in fibrocartilage, but what you can see are the fibers. So fibrocartilage is kind of like hyaline cartilage, but with bigger, thicker collagen fibers in it, which are going to make this stronger and more resistant to shear forces and tearing. So this is our kind of really tough cartilage. And we can see some chondrocytes within the matrix there. So since the fibers make this extra strong and somewhat flexible, this is found in two places. Our intervertebral discs, this forms the kind of outside of this, we call it an annulus fibrosus. There's also kind of a gooey nucleus pulposus in the center of our intervertebral discs. And then in our symphysis pubis. These two are both joints where we find this. Menisci are a little bit trickier. Menisci are in a joint, but they are not themselves a joint. But you have those within your knees, and if you think about running or something like that, your femur is going to kind of pound on the top of your tibia, and there is a fibrocartilaginous slab that actually forms kind of two cups for the ends of the femur to fit into, which helps to stabilize your knee and to cushion those blows that your knee takes during the day. So two joint surfaces and one other place which is part of a joint but isn't forming the joint itself. Our final cartilage is elastic cartilage. And here's where things get a little bit sketchy because we already had elastic connective tissue and your job is to not confuse the two. Well, how do we not confuse them? Elastic connective tissue has that fluid ground substance. It's not really going to be three-dimensional. That's how it fits into the walls of arteries and stretches and snaps back, kind of like the waistband of your undies. Elastic cartilage is a cartilage. We have that thicker, more solid ground substance. This is going to form a three-dimensional structure because cartilage tends to form thicker globs of material. So we still need to think, where do I need something that's going to stretch and snap back, but has to be kind of a three-dimensional structure? Reach up and grab your ear and bend it and let go. It's going to snap right back into place. So, because elastic cartilage can stretch and snap back, because cartilage is three-dimensional, this will form the auricle or pinna of our ear, and it also forms our epiglottis. This is kind of a spoon-shaped structure that's at the top of our voice box, which folds over during swallowing to make sure our food goes down our esophagus rather than our trachea. And when we are done swallowing, it can flip back up into position because it's made of elastic cartilage and it snaps back into shape. All right, we do have a couple different forms of bone to take a look at. Those are part of our supporting connective tissues as well. Here we can see a lacuna within the bone, but there are some bigger spaces in here, and they appear to have a bunch of red kind of circular structures in there. So it looks like we've got blood associated with this bone. The bone has multiple lacuna in it. We might even see kind of some lines in there as the bone layers are laid down. This is cancellous or spongy bone. And this has spaces within it for bone marrow, and it also helps make the inside of our bones light while still allowing them to be strong. So we find this inside bones. We find it in the epiphyses of our long bones, which is going to be the ends of that again. It ends up that in our long bones, like our femur, the big tube-shaped area called the diaphysis is going to be hollow on the inside. We call that the medullary cavity, although we do fill that with fat, which we refer to as yellow bone marrow. So this is an area where we're going to have space for what we call red bone marrow, which is where we form our blood cells. Now, it ends up that in most of our other smaller bones, they are filled with this cancellous bone on the inside. So if you were to take, say, the bones of your foot, those kind of square ones there, or of your wrist, and slice into those, there would be a thin layer of what we're going to call cortical or compact bone on the outside, and they would be filled with cancellous bone on the inside. All right, here we do see cortical bone, and this is obviously very solid material. Cortical bone is going to form the cortex, which is the outside. That's how it gets its name, but it is also sometimes called compact bone because of its lack of space and therefore its great strength. The other thing about this is by being solid, it can be relatively smooth, although we do still cover it with hyaline cartilage, a much smoother material on those joint surfaces. So this is kind of laid out with a central canal, and then these surrounding layers you can see here, like ring after ring after ring, called concentric lamellae. We can see the lacunae within that. This entire structure here, which is all of the concentric lamellae surrounding this central canal, is referred to as an osteon, and that is kind of the basic unit of cortical bone. So why do we find cortical bone where we find it? It's solid, it's strong, it forms the outside of bones, and of course that term cortical does come from cortex, which means the outside layer. Alright, so you might be saying, why in the heck are we looking at the esophagus and trachea? Well, I wanted to end this lecture, this actual combination of lectures on tissues, by taking a look at some actual organs, because as we think about the complexity of organization, we know that when we combine cells together and they work together, they are going to, of course, form a tissue. When multiple tissues are working together, they form an organ. When multiple organs work together, they form an organ system, and any individual is formed by organ systems that are working together. So we want to know exactly what an organ is and how it relates to tissue. We're seeing two organs here, the trachea and the esophagus. The lumen is the hollow space inside of each of these. When we think of trachea, it's held open by hyaline cartilage rings. And I can see that here in purple. There's going to be some areolar connective tissue between that and this thin purple layer here, which is the epithelium of the trachea. Now, if we think back, we know that, hey, my trachea is my windpipe. I breathe through that. I need mucus to capture particles. I need cilia to get that mucus out of there once it's done that. So I'm going to need a ciliated, pseudostratified, columnar epithelium in that particular location. When we think about an organ like the esophagus, it has a very different job. It doesn't need to be rigid. It doesn't need to stay open as we're breathing in and out. It needs to be muscular so it can force food from our throat down into our stomach. And there's a thick layer of smooth muscle here. And what that means is once we initiate swallowing in our throat using some voluntary skeletal muscle, that smooth muscle is going to make sure that that food makes it down to our stomach through involuntary contractions. Now, if we think about the lining of this, I'm not just passing air down through here, I'm passing food down through here. Think about the kind of stuff you eat. So maybe you're putting some Doritos or Takis down this. Maybe you're putting some bourbon down this, as I might do on occasion. Those kind of things are obviously going to damage a kind of less protective tissue. Think about the last time you drank soda or hard alcohol and laughed and blew it out your nose and it burned like crazy. Well, that's because you put those kind of materials on this kind of epithelium, the one that's supposed to just be having air running over it. In here, we actually have an epithelium in our esophagus, which is the non-keratinized stratified squamous epithelium. So it's going to be the most protective, the thickest material we can have on the inside of our body because we are passing food down this, and that certainly could contain pathogens or just things that might be abrasive. So anyway, that's kind of how we want to take a look at organs. And so we're going to go ahead and move on and to do a couple of chapters on bone and on skin, which help expand on what we've learned in the tissues chapter.